Good day, everybody. Today's International Industrial Ecology Day, an event that we organize online for the second time, which starts in Sydney, Australia at early or at midnight Universal Time, and ends at the US West Coast 23 hours later or so. And so my name is Edgar Hertwich. I'm a professor of industrial ecology at the Norwegian University of Science and Technology. The session is titled Cutting Edge Applications of Industrial Ecology in the Built Environment. Welcome. We are recording this session just for your information, and we will likely share this in a YouTube channel. I would like to welcome all my presenters and panelists, as well as the audience. The focus here is really on the use of industrial ecology in practice, and how we go from research to applications, and how these things become useful in practice. And I have a little story. Just the other day, I had a former student who sent me a message on LinkedIn, and she had graduated in the early days of our program, and she actually thanked me for starting, contributing to starting this. And said, well, now I do all this interesting stuff working for a municipality. I use life cycle assessment, and buildings are important, and we are reducing environmental impacts through these tools. And she was really glad to have that type of job, and finds it interesting that this has become so popular now. And a lot of our early students were actually sort of struggling to find a place, and it took a while before the wider building construction industry and the consultancies that are associated with that industry, and the municipalities that basically regulate construction discovered the tools. And of course, the current drive to reduce greenhouse gas emissions is an important cause for this interest in trying to understand what the environmental impacts of buildings and the infrastructure are. So we have assembled a group that consists of researchers, consultants, and people who work at organizations that are sort of intermediaries and advise policymakers and so on. And the first presenter today is Carine Lausselet. She has a PhD from the Industrial Ecology program at NTNU, where she worked with Helge Brattebø on the Zero Emission Neighborhood Research Center. And then she shifted to a position at SINTEF, which is a research organization in Trondheim, a large research organization. So she will give us the first presentation today. So I will give the word over to you, Carine, if you could share your presentation and your video.
Yeah, can you see my presentation in presenter mode?
Yes, we can.
Yeah, no, thank you very much, Edgar, for the opportunity to present. I do sincerely appreciate. So, as mentioned, I'm working at SINTEF in the Department of Architecture, Material and Construction. And recently, I became the research manager of the group of material and construction. So at SINTEF, we love to work to have this ecosystem view, and when we conduct research, ecosystem in terms of entrepreneur, public authorities, business, investors, and research. Just 2 words on my group. I talk to them every other day about the benefits of industrial ecology, so I thought it was fair enough just to to tell you a little bit why they are so important. So if I were to describe in one sentence what we do in my group, I will say we focus on the development of building materials, the use in construction, their durability and impact on the environment. So on the left side, you have the material side people with a very strong focus on cement and concrete. On the here you have the construction, so those materials going into the buildings. And here you have us, the industrial ecology people. Some of you may recognize some known faces here. Yeah, so it's really to go from the material to the building to the neighborhood, so that goes to the benefits as a society as a whole. The first case is going to be on the use of input-output and LCA, so hybrid LCA at the neighborhood scale. Here, this is a neighborhood located in Norway called Udalid. Yes, it's per today. It's not like it's look today. It's like it's going to look in maybe 10 years or so. So today it's only the kindergarten and the school that are built, and the residential part is going to be built over time. So if we have this neighborhood Udalid, and we want to conduct cutting-edge methods of industrial ecology on this. So the first thing to do is really to define the case study, so part 1. But then we developed together with Robert Crawford from the University of Melbourne and André Stefan as well in Belgium. We developed hybrid coefficients for each of the main materials by using the process-based database Ecology and as an input database Exaribase. And then the conventional step by multiplying those emissions intensities with the material to go from material to the building, and then to the building to the neighborhoods by adding everything also happening on the construction side. So if we look a little bit at the results, so here first on the material side on the y-axis we can see for the main main materials, timber product, plastic, metal, insulation, plaster product, and concrete. And on x-axis we can see the contribution of the process data and EO data. So we can see that the proportion of the input-output data varies from 10 to 78%, with an average of 34 and a median of 24. So what we can see as well is the materials that have their emission more spread along the value chains have a higher trocation error or a higher share of input-output data, which is the case, for example, for gypsum plasterboard. The opposite is true for materials such as concrete, who has a very high share of direct emission, and those type of material are pretty well covered with process data. Then if we take those material to the building level, and then we add a bit of regulation in terms of construction standard, in terms of environmental assessment of building, then we have the typical life cycle stages. So product stage A1, A3, the material, then transport of the material to the construction site, A4, everything happening on the construction site, A5, and then the material replacement over time, B4. But then what we found out is that those standards are based on process LCA, and then they cover a fair share of the emission happening on the construction site and on the building, on the construction of the neighborhood, but they don't cover all emissions. And in fact, we added a new category called others, which account for 40% of the overall emissions. If we go on with the same neighborhood Idalier, but this time we combine MFA and LCA. So if we take Idalier with the kindergarten, school, and residential area to be built, and then we applied, I would say, conventional building stock dynamic over time with the typical construction, renovation, and demolition activities over time in part 1, and then in part 2. On the right-hand side, then we add, on top of that, we add very detailed material inventories per each building type. And then for each material, we add emission intensity. In order to have, in part 3, the material flow over time, as well as the emission flow over time. And then for this neighborhood A-Daliet, this is how the emission storyline, if you wish, will look over time. And then in order to make the result be more digestible, we group, of course, the different type of materials in the main groups, but this is how we can potentially look like. So what we can really see in the baseline scenarios, we can really see this peak of emission at the beginning, which accounts for 40–50% of the overall emission, and then the emissions spread a bit more over time. And if we apply material efficient strategies in terms of more intensive use, lifetime extension, improving yield in production, then we can see the following benefits. So at the beginning of the lifetime of the neighborhood, which is in year 2030, where the whole neighborhood is built, then you can really see this peak of emission induced by the construction of these buildings. But if you use, for example, a more intensive use strategy, such as reducing the floor area per person in terms of building area, then you can already decrease this peak of emission. If you're a bit more careful in the material choice, then you can again decrease this peak. And then over time, then we go a little bit more in B, lifetime extension, in terms of material lifetime extension, but also the building as a whole. Then we can again decrease a little bit those emissions over time. And then improving yield in production, it is more, it goes to the material production today, but also over time, so they can decrease again. And then last case I wanted to show you was on the use of MFA and LCA at municipality scale, with a bit of a wider scale this time. So from the building to the neighborhood to the municipality. So this, if you have Norway, Trondheim, and then you have this case here called knowledge axis in Trondheim. I'm located in Trondheim, just for the information. And then again, this case, and then we apply MFA technique over time. So building stock for each of the different type of building. We had 20 or so type of building, residential, but also service buildings. And then again, we apply construction, renovation, demolition over time. We have geo-reference the building stock by using cadastral data, and I'm going to show you on this next slide why it was so important. And then on this building stock, we added the energy demand combined with the technology efficiency in order to have the energy use over time and the related greenhouse gas emission intensity for each energy carriers, but also for the material use in terms of the new construction, but also renovation over time. And then for this particular case, we have the results, part of the result. It was really the idea that we could really go to a municipality to really show their municipality and how it will evolve over time in terms of building type first, but also in terms of development. We had very close contact with them in order to understand which areas of the municipality will develop over time, and also in terms of what type of building. So this is shown in this first heat map. And then in the second heat map, then you can really see the energy use over time based on different scenarios that I will not go into detail now, but you can really refer to this study if you want to know a bit more. But really, it was really the use of MFA, LCA over time, and also I think very powerful use of heat maps to show the results. Thank you for your attention.
Well, thanks a lot, Carine. It was really interesting to see how this develops your tools to actually display the emissions of buildings that are spatially located and to develop these scenarios of urban space. So we're going to have opportunity to ask questions and engage in a discussion after the first 4 speakers. So I'll go right to the next speaker, and this is Freja Rasmussen. Freja is a postdoc at Aalborg University today. Tomorrow she will start as assistant professor in civil engineering at NTNU. She will tell us about applied building LCA in Denmark. Research meets practice meets regulation, and this is really about setting developing standards and making standards mandatory or not, and that important question. So if you could share your presentation, Freja. I think, Carine, you need to get out of your presentation, right? And then we can see Freja's presentation. And over to you.
Thanks, Edgar. I guess it's there now. Right?
Yes, it is.
Yes.
And by the way, there is a Q&A, and I think the first question is still to Carine. So that if you write Q&As, I think it's good if you're more specific who you're addressing your question to. Thank you.
Okay, yes, thanks for the introduction, Edgar, and for having me here today. I'll give you a brief introduction to how LCA has been integrated into the Danish building regulation, or how it's about to be, which is something I've been involved with quite intensely for the past couple of years. Yes, so for now I'm affiliated with Aalborg University. Tomorrow it will be NTNU. So we all know about the significant environmental and climate impacts from the building and construction industry. And for a long time, this has been dealt with, at least in Danish conditions, by voluntary means. So building practitioners has engaged with these green certification systems such as DGNB or BREEAM, where LCA is part of the larger sort of pool of criteria that are assessed as part of obtaining these certifications. And now, in the past couple of years, we've moved into a phase where it's becoming more of a thing that's a mandatory thing in several countries, not only Denmark. So there has been a documentation requirement in the Netherlands for several years. Niko will tell about how it has been implemented in the city of Zurich as well. So on different scales, it has been introduced already. And of course, sort of what the building designers and practitioners want to know is how to minimize the greenhouse gas emissions associated with one project or another. And the ones of us working with LCA in detail in our everyday life, of course, we know it's not that easy to point to the best low emission building design, because there are several choices, several options that determines what the best solution is, whether it's recycled materials, whether it's zero energy use, densification. Several strategies are in place. And sort of the answer depends on how. So the answer to what the low emission building design is depends on, for instance, how you allocate between systems, how you define your system and the substitutions in the system, how you account for or do not account for the biogenic uptake and release, which life cycle stages are included, how much of the building do you include as part of the inventory. And then also, of course, about the data you use, just as Carine showed, whether it's bottom-up process-based or it's hybrid. So it's not easy to come up with an exact answer on which is the right building to build. And that's also difficult to put into the regulation then. And of course, we do have a standardized approach to define to approaching the LCA of buildings via these EN 15978 standards that defines what we determine as part of the different life cycle stages. But still a lot of room for interpretation in this standard as well. So a lot of our research, what I've done with Aalborg University, has been focused on sort of this rather gentle demand from the building sector, and also cooperating with the authorities on establishing these voluntary measures. And so we've been interacting about what could be a method that is not to put too much work on the industry, because if it's voluntary, then it really matters how many working hours they put into it, of course. Also making sure that we push to the product data side, so we get more information about the different products on the market. And then also what we have been working with is also providing tools freely available for the industry, so it can actually, so it's easier to implement in their practice. Now, moving into this new phase with regulation, we've had a quite significant change to the way we've worked. So this is the policymakers in Denmark when they decided, maybe it's 2 years ago, that LCA documentation and limit values should be part of the building regulations from 2023. So starting in just 1 month. So that really put a stress on the demand. Suddenly, everyone in the industry knew they had to cope with this within a few years and had to deal with it in the way they did the processes and the way they did their assessment. So especially this thing about integrating limit values puts a pressure on how we then establish the method, because in the policy-making process, they would look into the research that we had done in the building area, and they would say, okay, we find this number here in your reports about the median value of buildings being around 13 or 14 kilograms of CO2 equivalents per square meter per year. Could we just set this limit value a bit lower, and then we would make an improvement to the future buildings if it's in the regulation? And then they decided on this number, and now it's just a very fixed thing in the regulation that we have to deal with when trying to moderate the method, because of course we did not have the perfect method in place at this point in time where it was all voluntary. But they had to base their political intervention on something. So they built it on that. It's not that it's an totally imperfect method, but we could improve it, and we would like to improve it. But now, as with this policy process, it's really hard to pull any handles, because it's quite locked. We're locked into one method. We're locked into one type of product data because of these limit values. So that's an interesting place to be, to find out how much can we actually change, or how little can we change in the current situation. And when do we then have the opportunity to try to push these changes on the method and the data through? But anyway, now we have the established method for the Danish building regulation to come into place in a very short time. So now based on the method, we don't have all these open questions now, because now we just point to the method and say, well, these are the rules. These are the rules we will follow, at least for the next 2 years. But it would be odd if we changed the rules a lot for the next revision of the regulation. And so the point is that as a researcher, it's quite difficult to be in this policy environment where things are pretty sort of tightly set, because we usually want to take in several perspectives and maybe another system boundary and another perspective of scale. But this is really a new discipline for us. So it's a balancing act, and it's also about, I think it's about research integrity. How much can I cope with these compromises that we have to do between what we would like to have in the research, and it's also, of course, it's also positive that it's being implemented and used. But yeah, so the last point is that we shouldn't just settle with what there is now, but also keep trying to push the improvements to methods and data, and challenge what's in place. That was it. So I welcome any questions and look forward to the debate afterwards.
Yes, it looks like there's a question already on the Q&A for you to answer.
Yep.
And so thank you, Freja. This is quite nerve-wracking, right? When suddenly your science comes under scrutiny by practitioners because it means something, right? And they have to actually adapt to whatever you find. And then you say, well, there's still some uncertainty in the methods. And the fact that this now becomes a standard really means that it, in some sense, it gives you a lot less flexibility on the scientific side. And of course, that's something we cannot avoid, right? And so as soon as it becomes important for the outside, I think it's quite clear that happens. So now we have had a case of a researcher who has worked on developing standards. So now the next case is a researcher who has gone over into practice and actually the use of these tools and methods in the city of Zurich. And so over to Niko Heeren, who has a PhD from ETH Zurich and spent some time at Yale University as a postdoc and now works for the city of Zurich. And so please, Niko.
Thank you very much, Edgar. Guess it's the perfect transition from Freja's presentation. I'm the guy who's being held responsible when we don't meet the net zero targets in the city of Zurich. I'm the team lead for the sustainable construction section in the construction department of the city of Zurich. And yeah, I'm an industrial ecologist who has turned a little bit on the administration side of things. And so today I want to talk about the goal, net zero, the goal that the city of Zurich has established for itself. I will give you a bit more details in a minute, but maybe shortly about what we do. So we are a little bit in an awkward spot. We are basically the interface between the building owners, the building users, and the architects and the planners. So we are kind of the building owner representative responsible for carrying out any construction projects of city-owned property. We are quite a large office, and there was in Zurich, it's important to know, there was already a referendum in 2008 where the so-called 2000 Watt Society, also a climate goal, was accepted by the public. And this is when our sustainable construction group was founded. And we've been working with 7 people on this issue. And we developed quite some knowledge and expertise in this field. So what do? We like to think in our sustainable construction section, we like to think that we pioneered recycling concrete in Switzerland. We really pushed forward that recycling concrete is becoming a standard for basically all of our construction projects. We are using recycling concrete now. We are also pushing forward LCA. So we are pushing forward the development of LCA databases. So there's the so-called KBOB LCA database. It's something like a sister database of the Ecoment database, not as well known, but certainly worth taking a look at for any construction practitioners here in the call. We define and we set the goals that are in line with the city's climate goals. So we have, for instance, for our construction projects, we have clear and actionable standards that we set for every construction project, and we also control. And we are piloting a lot of pilot cases and research projects in an applied sense. So, for instance, we have 3 construction projects where we are trying to use reused building components. I very quickly during Freja's talk also put this triangle here. She was talking about the 12 kilogram CO2, or should be lower too. So we are also controlling each and every of our construction projects. Green bubbles means it's refurbishment projects that we've carried out. Blue bubbles means it's new construction projects. The further to the right, the more emissions we have from material. The further up, the more emissions we have from the energy demand. This is really my favorite slide. I will come back to that in another minute. But we also, like, as I said, we set the standards. We have the 12 kilogram. We have had that for quite a while. And we are also seeing how we can actually get there with our construction projects. So yeah, the net zero target, it is something that really came from the pressure of the street during the climate strike movements. So already last year, the city council decided for the city administration to come up with net zero goals. So for direct emissions, so within the city parameters, the city administration has to go net zero by 2035, which is everybody who does construction is like basically tomorrow. We also have a goal for indirect emissions. Not every city that has a net zero goal has also indirect emissions covered. We have one that is minus 30% until 2035. And very recently there was the referendum. So the people actually voted to also have a net zero vision until 2040, which covers the whole population and all the other consumption sectors. I guess in this audience, it's not really necessary to talk a lot about the relevance of material and embodied emissions, but I think it's really very important to keep in mind that this is the elephant in the room. I think the city especially has done a lot of district heating and so on. So I think energy supply has been mostly decarbonized in the last years, and the real issue is becoming the construction material. Also in Switzerland, there is no legislation on embodied emissions, and I don't know any country where it is the case yet. I think this is still a huge issue we have to tackle. Something we are looking into in that context, because net zero also means you have negative emissions, right? Because you have your positive emissions, you subtract the negative emissions. We are also looking at that, and we all know 1.5 degree is the target. Just a reminder, we're basically already there. We will probably overshoot anyway. But there is different research projects. This is an interesting paper by Matthews et al., where they look at the impact or the benefit of negative emissions from carbon storage. There is an effect, but it is not maybe as pronounced as we may hope for. But we are also looking at the feasibility of storing carbon in the building sector. So really, my issue is I'm a little bit at the interface. I'm of the different stakeholders in the construction project. So we have the policy, we have the building owners, we have the building practitioners, the users, the schools, and so on. And we are really trying to come up with a process where we can get everybody in the boat and see where the responsibilities are to get to this net zero target by 2035. And our idea was to basically produce a calculation tool which we can use on the spot with the different stakeholders. And we identified a bunch of different strategies that we implemented in this calculation tools. So the different strategies, I don't want to go into a lot of detail because we don't have the time here, but we're looking at like refurbishment, so doing less new construction as opposed to refurbishments, just using less square meter per person, doing more material efficiency, so doing more with the material we are using. Wood construction is certainly an important lever, and so on. All of these measures, we have some studies and did some plausibility checks. We have an estimated potential, and we also looked at the time horizon we think these measures can be implemented in. Just one example, again, my favorite slide. So one example is the doing more refurbishments as opposed to new construction. So in a city, we always have the potential to densify our city, meaning, we can top up existing buildings instead of, doing a tabula rasa project. And we really see that the benefit is really tremendous in terms, at least for material. We have an average, we see something like 10 kilograms per square meter a year from new constructions, as opposed to roughly 4 kilograms for refurbishment projects. So these kind of numbers we put into our Excel calculation tool, where we have these different strategies implemented. It's much less refined than what Carine showed us just earlier. It's really a very simple Excel tool. We did that on purpose because we wanted to have it available very quickly. And it's really the idea is to have something we can apply in the discussion with the different stakeholders. What we do now is we can look at different development pathways. So how many schools are we going to build? How many housing we will have to provide to the community, and so on. And there we can test the different strategies. So very similar to what Carine showed us earlier, we can now test like, okay, if we do wood construction, how much closer to our target by 2035 will that get us? And the problem is really like we have these shared responsibilities. So we have the architects that can maybe use less materials. We have the industry that can provide us with CO2-free steel maybe one day. We have the building owners that it's only them who can decide to use less square meter per person or per school children. So we have these different shared responsibilities, and that tool helps us to, in the discussion say like, okay, how much, guys, do you think you can reduce the square meter per person? We try to answer the question like, what is the upstream emissions from future construction material and so on. This is really an ongoing process, so please don't cite me on any of these numbers and results, but something very interesting I found in using this tool is we all these green measures, which is wood construction or doing more refurbishments and more material efficiency. These are basically, in my opinion, these are measures that are available already today. When we look at what the construction or material industry can do, that is maybe more this yellow part here. I would argue, CO2-free steel will not be available before 2030. And, the combined effect of everything, all of these instant measures we have available is when you combine it, the reduction in the cumulative emissions over time is at least as pronounced as it is what we can expect from the industry. So that is my statement, like, okay, whatever we can do, we have to do today. Sufficiency, more refurbishments and so on, because we can't wait for industry to give us the one-fits-all solution. So that brings me already to my conclusions. I think, these new climate goals, they require a mix of all options we have on the table. I think, the building owners sometimes have the notion that, we just order CO2-free buildings, but that won't work. Material efficiency is a very important instant measure, something we can apply basically today. It requires much more of a collaboration than we've seen in the past, and it really takes everybody on the table to make important decisions. I think it was a good learning curve for us to create this tool, to use that in the discussion and to see who can contribute what. So it's facilitating this dialogue. And yeah, a message to all of you, like, push your governments to finally regulate embodied emissions. Yeah, that's it from my side today. I'm happy to take your questions later on.
Hey, Niko, it looks like you have a really interesting job. So I'm glad to hear about all the progress that Zurich is making. And I remember when I started out looking at LCAs of buildings, it was really 80% to 90% of the emissions were associated with the energy use in the use phase, right? And so it's both energy efficiency and the tremendous progress that has been made in decarbonizing the energy system that we already see as an important result today. And this is, of course, the first order, what governments should do first. But as you point out, that some of these measures that industrial ecology suggests are also low-hanging fruits and can be implemented quite as quickly. I would like to go over to the next speaker. So Oddbjørn Dahlstrøm Andvik graduated from the master program of industrial ecology at NTNU 10 years ago, and I just looked up because he and another student, Carine Lausselet, together wrote a scientific article which was published in Energy and Buildings in 2012, the first LCA of a passive house in Norway, and he went right on to an engineering consulting company, Asplan Viak, where he still works. And he has been practicing what he has learned in school, and that's of course something that we also are proud to see. So over to you, Oddbjørn.
Hello, can you hear me?
Can hear
yes.
You well, yes.
Thank you for the introduction, Edgar, and it's nice to be here today, and thank you for inviting me. I will share my screen. Now you can see the screen.
Yes, we can.
Yes, nice to be here. And I will today talk about from the theory from NTNU and LCA to EPD, and how we use this information in the practical everyday life, working as a consultant, and how we can use that to help our clients to make the best environmental decisions. And my background is, as Edgar said, I have a bachelor's in logistics engineering from Trondheim and from an industrial ecology in Trondheim in 2011. And I work as an advisor or consultant in Asplan Viak with the field of energy and environment. And usually it's most LCA of buildings, rail, roads and roads, but also in the making of EPDs and use of EPDs to the clients to see the how the different products can affect the buildings and the material used in the buildings. I will assume that many of you know what an EPD is, but very briefly, an EPD is a type 3 eco-label third-party verified document based on LCA, and that declares the potential environmental impact of product and services. It's a standardized and objective practice that ensures comparability and transparency between the different producers of building materials. And this provides the necessary documentation of green public procurement. At least in Norway, we have in the last years seen the focus and our trend to have requirements on CO2 emissions when we buy products and materials. And then an EPD can then be the document that describes the how this product or that product is compared to the procurement. And the main reason is not just to document the environmental profile, but it's also to give the manufacturers insight to their own productions, find the hotspots, how they can be better in the future, and what they should focus on when they want to invest to reduce emissions. In Norway, we have EPD Norge that is in charge of all the EPDs, and recently we have EPD Norge has got over 2,000 published EPDs. EPDs are mostly on building materials, but also furniture and energy systems and other kinds of non-building materials are also in the future the focus of EPDs. This is an overview of an EPD. You have a front page for a specified producer and a product, and some general information of what the EPD content is. This is, for an example, 1 cubic meter of timber, and then a description of the LCA calculation rules, how the LCA is made for that EPD. I will not go into detail, but all EPDs are available online, so it's available to find much information online. It's more like for food nutrition facts. You can see the content of that food product or the content of that building product. What is the LCA environmental impact in global warming potential and other impact categories to produce 1 cubic meter of wood or 1 cubic meter of concrete and so on. When we are doing LCA and carbon footprint of buildings simplified, we need to know the amount of materials to build that building and the emission factor of that material. In sum, all of that will be the carbon footprint of that building. The amount of materials, we can work with architects and engineers to reduce amounts and maybe change from that product to this product, and also to see the function if could we have more people working in the office space by share office, for example, increase opening hours of the store and so on to use the built environment as much as possible. But when the architects and engineers have decided that the building design, we need to find the best materials available to build that building, and then we need emission factors. Then you can use the databases, Econvent, for example, or EPDs. And the best way then is to use find EPDs, compare producers, and then find the product that is best to build that building. As an example, we have been involved in making many EPDs, and here's an example for natural stone. The functional unit then is what is the emissions or impact category impacts to make 1 ton of natural stone. Then we went to different producers and found a complete list of energy and materials to produce that amount of stone, and divided all the inputs and waste for all the produced products. We went through the quarry to see what is actually being doing in the quarry, which machinery are you using, how can you make the mountain to actually products in the building, to the production site. At least for natural stone, it's a large amount of handwork and not so heavy machinery, so people are working with the stone by hand. And then to a flow chart, we need to convert that from products manufacturer to more or less how we can do that in LCA. What is the material and energy input? What is the waste? Through all the life cycle of that production. And this is could be simplified, but you have all allocation problems. You can have maybe problems to find what is up in the value chain, which products are you buying. Usually the companies have good control of energy use, but further upstream in the value chain could be quite difficult to find details. And then to the LCA results in the EPD. So to produce 1 ton of natural stone, it's about 86 kilograms of CO2 equivalents. Another example is for a building. This is the emissions for a building we have worked with in global warming potential for the building parts, foundations, structural frame, and so on. And then the goal was how could this building be built the best way possible with the lowest emissions possible. As you can see, the slabs, concrete slabs, is around 24% of the total emissions, and the solar panels, PV panels, is around 17%. And around the 75% of the emissions is from constructing the building, and so it's important to have focus on the slabs, concrete, the PV panels, and the construction phase to find hotspots where to reduce the impacts. This calculation is in the start based on database numbers for PV panels because we didn't have any EPDs. But we have been working with PV panel producers to make EPDs for a PV panel, and we found out that in the value chain of PV panel, it is the wafer and the solar grade silicon that is maybe 80% of the total emissions of PV panel. So then we have also worked with the producers of solar grade silicon, and to the left you can see that the column to the left is database number for silicon, and the column to the right is producer, EPD producer of silicon. It's around 80% reduction to have company specific data compared to database. The same we can see with wafer. If we use then this EPD number in the wafer production, we can also have a huge reduction compared to the database numbers and also to the PV panel. So from around 200 kilograms of CO2 per square meters panel, we can find an EPD producer of PV panels to go over 50% lower than the database number of PV panel. using that number back again in the calculations, then we can reduce this PV panel numbers by around 50%, and this will reduce the building carbon footprint of 9%. Working like this in all the different building parts and all the materials, we can then find the best way to reduce the emissions of the building, and then always be in front of requiring the best materials in the procurement also. So briefly, from LCA to EPD, we use LCA as a tool for producers of building materials. We go to the producers, conduct LCA, make EPDs, find hotspots, where should you invest your money to have the highest environmental reduction, and then document that in an EPD. So the producer can use that in the procurement later on, and as being the best producer as possible. This was this. Thank you for your attention.
Thank you, Oddbjørn. Very interesting. I'm just wondering, and now we can start a discussion amongst all the speakers. You know, I think what you show is that numbers are, you know, they can change, and of course, photovoltaics is a technology that has undergone a tremendous development, and the costs have come down to levels that we had never expected, right? And one of the mechanisms by which costs come down is, of course, that the amounts of materials become less, wafers become thinner, and the other mechanism is that the processes become more efficient because you have sort of economies of scale. And I think all of those things are probably happening here. And that's the background for why you see these emissions decreasing so much. Hopefully, it's not the choices of your system boundary that are different or something like that. And so I think it raises a question, and that is the data good enough, right? And is it good enough for the decisions that we need to take? And I think what you have shown is this tremendous development of the number of EPDs that exist for buildings and building components. And that's, of course, demand driven, but it's also supply driven if there are companies that want to sell their products and get an advantage having this product declaration, because some customers are actually looking for low emissions components and materials. And so I just want to throw this out to all of you. You know, is the data good enough? Are we learning something from the data becoming better? And or is there still so much uncertainty on these LCAs in terms of the specific system boundaries and methods and assumptions that it's really hard to compare those numbers to each other?
Maybe a quick thought from my side. Sorry, Freja, for jumping just ahead the queue. Because we have the same issue. So in Switzerland, there is this KBOB list I mentioned with LCA data, which is extremely useful to us. And it's generic data. It's intentional generic data, like there's only one concrete or one steel beam and so on. But producers can come with their EPDs and have them like reevaluated and get them in there. But something we see is that the EPDs, the quality of EPDs differs so much. So I would kind of reiterate your question, ask, is EPD good enough for us?
Any thoughts from the others, Freja?
Yeah, just kind of along the same line, I guess. It's the one piece of data may not be good enough, so we would need to work with ranges instead of just putting all our trust into one piece of data on this one product. And I think one of the key messages from what we've seen in our research is also that it doesn't matter whether you choose one or the other fiberboard plate for your building. It doesn't matter how you design the building and whether you choose to, and how you use it, and and whether you choose to go for a whole other material composition. So it's not the same product against the same product type, and then comparing the EPDs. It's like larger decisions where it makes sense.
So in some sense, it might not be the precise number that is important, but to give you the right order of magnitude, and then the architect or designer or the customer really needs to make decisions on how to reduce the amount of components or materials that cause a lot of emissions, right?
But it's the problem with numbers, right? Because the practitioners, they look at the numbers on the different kinds of fiberboard plates, and they see, well, one is 3.2 and the other is 3.4, and then they choose the first one, and they think they're making a good decision, and it's not what matters.
I know Carine has also worked with EPDs, at least SINTEF is using them extensively in CEN. I think my question, because Niko has said that the quality of EPDs is very different. As an expert, can you look at an EPD and recognize whether it's good quality or not? Because you don't see the inventory, right? Behind it, you don't have the ability to inspect that at the unit process level. Is anybody who wants to answer that question?
In fact, we have a study where we compare the use of EPDs and equipment data to see the differences. But yeah, it really depends. But I had a comment on the good enough on the use of data. Now we have a case with the Trondheim commune again, a municipality of Trondheim, where we had them to really create a guide and a template to report their greenhouse gas emission for new buildings and infrastructure projects. And I was thinking about you, Niko, when you show your template. I think it's very, very well done. So I will have a talk with you. But then we are really wondering about the level of detail on those data. And if there is no data, then what do you do, and which reference do you use? And then with the question, is it better to have a fair enough good data or to have no data? That's also a bit the question.
Okay, good. Over to you, Niko.
Yeah, just to maybe partly answer your initial question. Something I'm observing really is that the market or the industry has started moving a lot, like quickly now, and I think that was kind of the argument by Freja also. We see that like now the fancy architects, they do like, net zero buildings and so on, and they bring a lot of creativity to the table, and they're not afraid of trying new stuff. And so we've recently seen this presentation where they use straw as insulation material, adobe for the floors and so on. And then when I look at my LCA lists, I'm like, oh, I don't have data for that. I don't have. So I think, especially for new material and innovative materials, there's certainly a demand for new inventories. Yeah.
All right, Oddbjørn. Unmute yourself, exactly.
Now I'm unmuted. I totally agree that uncertainty in the EPDs could be quite, it's a big uncertainty in the different EPDs. You have, at least for PV panels, that the development in the production is changing almost every year or month. So to have an EPD that is 5 years old, it could be not a good number to use in the calculations. And at least we should be focused more on having the uncertainty in the calculations shown than just not a number that this is better than this, because you know that it depends on the allocations and the system boundaries and everything that could be put into the EPD. But on the other hand, EPDs is a product that is more and more 2000 numbers in Norway, and we have EPDs in the whole Europe. So how to address the uncertainty in EPDs should be discussed maybe a bit more, and we should have this common knowledge, and not just that this EPD is good or good enough.
Right. So a short interjection from Freja, and then we'll go to the next round of presentations. You need to unmute yourself.
Yes, just a brief comment on the creativity of the industry, because when doing the EPDs, the producers are also becoming experts in how the rules are set up and where the loopholes are in the standards. And so we've seen EPDs where the production has reduced, the greenhouse gas emissions from production has reduced drastically because the company buys biogas certificates for the natural gas processes. And so it really requires some expertise to look behind the numbers in some of the EPDs.
Right, and it's a good question. You know, what are the emission reductions that we can expect from those things? And okay, very good. I think this was a nice discussion that we had. So we'll have now 3 new presentations. And for the audience, please feel free to use the Q&A function. If somebody in the audience at the end wants to sort of join our discussion, I can promote you to a panelist. If you send me a message through the Q&A, then that could also be a possibility. So the next presenter is Sahin Akin. He is an architect from Turkey who is currently a PhD student at NTNU, as you can see, and he will talk about his PhD work, which looks at resource consumption of affluent Arab countries that we all focus on right now with the World Cup going on. And you see the fantastic buildings already when you see at these broadcasts. And so we are trying to figure out what the environmental impacts are of those buildings and how to reduce them in the future. So over to you, Sahin. Please share your screen. And
yeah, thank you so much for the introduction, Edgar.
Yeah, we are in the presenters mode right now.
Okay.
I think if you just
can you see it?
Yeah,
right
now
now
it's correct. Very good.
Okay, yeah. Thank you so much for the introduction, Edgar. My name is Sahin Akin. Currently, I'm a PhD student in the Industrial Ecology program at Norway University of Science and Technology. I'm working with Edgar, Daniel Müller, and Niko in my PhD. As you all know, that building stocks are quite heterogeneous across countries and changes between different countries. The reason for that can be explained with their historical past, the fashion in architecture, their cultural past, human behaviors, their wealth and economical prosperities, and also the climate conditions of the geographic locations. In today's talk, I will talk mainly about the Gulf cooperation countries, which are consisted of Kuwait, Bahrain, United Arab Emirates, Saudi Arabia, Oman, and Qatar. Almost all of them are located in the Earth's desert belt, which are considered as the hottest places on Earth. And for that reason, they are going to be quite vulnerable to climate change with the global warming, because the households are consuming a lot of energy to cool down their buildings. Almost 70% of the secondary energy usage are related with the cooling loads in those households. And after the discovery of oil, the high population and urbanization growth rate is threatening the cities. The cities are expanded to further extents. And because of the oil, they are become one of the wealthiest countries in the world. When we just look into the GDP per capita, those countries are ranked in the top 10 mostly, which also affects the energy consumption in those countries. because they can afford using much electricity, and there is also some political wormholes, loopholes that are including some subsidies in electricity. Some of the countries has using the cheapest electricity in the world, and which is has a reverse effect in the consumption. And in my study, I'm looking for investigation of the typical building characteristics in these countries. What are the differences between those countries? What are the energy consumption and the material consumption of those buildings? It comes with a lot of challenges because the building stock needs to be modeled. But compared to European databases and European countries, there is a limited research in the literature focusing on these countries. And also the cadastral codes, energy bills, conducted surveys, GIS database and questions are quite limited. And also the building energy consumption is put it on primary focus on recently. So in order to answer the questions, we are following a bottom-up archetype development process. An archetype takes into account of individual building characteristics and groups them under some overarching archetypes, which are representative of the building stocks, rather than modeling entire building stock one by one. Instead, we are using archetypes to ease the process of modeling. So an archetype is represented with 4 different pillars, including form, which is focused on geometrical aspects. The second one is the envelope of a building, like including walls, floors. And third one is the system, such as the HVAC system, the conditioning mechanical equipments of the system of the building. And the last one is the occupancy behavior, including the operation. In the literature, there are different ways of model the reference buildings. The first one starts with literature sources and available data, and all of them are examined with expert team. And a theoretical reference building is created. The second approach starts with the actual building stock by selecting actual building, and with the expert census, a real building can be used for an archetype. And the third approach is combine all of those data at hand and create a theoretical reference building. I'm following the third one in my studies. After you have the archetypes, then you need to start the creating of the energy model. In order to do that, you need a lot of data corresponding to different building pillars. And those data can be grouped on segmented into different factors. And those factors are enriched with a lot of technical data. And afterwards, the last stage is the form creation. For the form creation, both qualitative information within the historical text and also some diagrams in literature, the floor layouts, some statistics related to the building stories and the areas, and some visual guidance about the building stocks can be harmonized. And based on the different fashions throughout the years, different cohorts has different kind of characteristics throughout the history. And after assigning the relevant construction materials into buildings envelope elements, we can have the 3D model, which can be used to conduct simulations and to calculate the energy and material intensities. So currently in our data set, we have 161 archetypes, and the majority of them are located in Qatar and Bahrain. A majority of them are located in United Arab Emirates and Saudi Arabia. And after you have the energy models of countries, we are using a Building framework. Building stands for Building Material Energy Software Framework, which is developed by Niko Heeren. It uses the Energy Plus and allows you to conduct batch simulations for energy and material intensities. You can conduct simulations for different combination of standards, climate zones, and different typologies. And the results are calculated automatically and is presented in a nice way. And this framework has been recently used in United Nations Environmental Program in the Resource Efficiency and Climate Change report. And for further information, you can scan the QR code or contact Niko about the Building for further collaboration or for your own use. So after we completed the simulations, it is also possible to examine in detailed way for individual models. You can make comparisons for different cohorts, compare different typologies, how they're performing in terms of energy and material. You can see the urban and rural settlements trends. You can see the city administrative levels trends and what their buildings are actually consisted of, and the country's performance. So since Saudi Arabia has much more population, which is followed by United Arab Emirates, they have a higher consumption. But once we examine the per capita results, Kuwait, Qatar, and Bahrain, which considered as small countries, are actually using 3 times more than a regular everyday citizen, which is quite striking. And apart from that, same energy models can be used for LCA calculations for understanding the environmental impacts. And also in the further stages, scenarios can be developed by using the dynamic stock modeling tools. Thank you so much.
Thank you, Sahin. Nice to get some background on the region that some of us are spending some attention to right now. So the next speaker will be Mie Fuglseth, and she has a master degree in industrial ecology from or in energy and environment from NTNU, and her supervisor was Helge Brattebø, and Oddbjørn was also involved in her master project. I found out she has spent 8 years at Asplan Viak with Oddbjørn and has recently taken up a new position as a senior advisor on climate and materials for the Green Building Alliance in Norway. And so it is over to you, Mie.
Thank you, Edgar. So I'll share my screen. Here we go. So thank you for the introduction. As Edgar said, I work in the Norwegian Green Building Council. I previously worked at Asplan Viak as a consultant, and I'm going to talk about a report that I worked on there. And the title of my presentation is Old as the New, because I'm going to talk about the role of the existing building stock as a carbon mitigation measure. And in this study, we looked at 24 different buildings. As you can see, that they are very different indeed, from very small sheds to large factory buildings, municipal buildings, etc. They have different ages, different construction methods, and the commonality between all the buildings is that they have some sort of cultural heritage value and the premise for the study was that this value should be preserved, and we looked at how we might refurbish and renovate these buildings in order to increase the energy efficiency and then the climate benefit. So we looked at 3 different main scenarios. One scenario, we don't do anything, just continue operation in the current state without any measures. Then a retrofit scenario with targeted energy efficiency measures that were also in accordance with preservation of the cultural heritage values, meaning that we didn't want to change the architecture or the external expression of the buildings too much. And we also looked at demolishing the existing buildings theoretically and erecting new modern buildings according to the current building code. And the main question we wanted to look at is when preservation and retrofit of older buildings is not only a cultural heritage measure, but also a climate mitigation measure. New buildings are becoming increasingly energy efficient, in large part due to stricter energy regulations. And also we are using more materials, not only due to energy efficiency, but also other technical requirements, which means that the importance of materials for greenhouse gas emissions is increasing both in relative and in absolute terms. This is mainly for new buildings. When we looked at the results from the assessment of the 24 existing buildings, we saw that for the retrofit scenario, and obviously also for the current state scenario, the energy demand and the energy use over the life cycle is still the most important factor contributing to greenhouse gas emissions, which led us to conclude that reducing energy demand is the single most important measure for reducing the carbon footprint of older buildings. As you can see, we also looked at different variations of the new construction scenario, both the standard building and a building with focus on low carbon materials, and also a passive house scenario. So when we say targeted energy efficiency measures, what does that mean? Well, in most cases, energy retrofit of older buildings will be a trade-off between achieving a modern energy standard, but also preserving the building's original expression and qualities. That means that we, as far as possible, did not assume that we were going to carry out an external reinstallation of the buildings in order to not change the facade and the architectural expression of the buildings. But we instead assumed a lot of different smaller, gentler measures for reducing the heat loss in the construction, and also increasing the efficiency of the heating system, i.e. changing from regular convection panel heaters to ground heat pump. And also for the non-residential buildings, we looked at how we might optimize operational performance of the ventilation and heating systems. On average, for these gentle measures, we found that you could achieve actually quite significant energy savings, on average about 40% across the different buildings. The extent, of course, of the different energy efficiency measures and the efficiency of the energy system were very important factors that contributed to the energy savings and climate benefits. But in essence, the analysis shows that you might achieve significant emissions and energy savings through these gentle measures that do not compromise cultural heritage value. So actually, for the majority of the buildings that we looked at, the carbon footprint was lowest for the retrofit scenario. 12 buildings where the upgrade or the retrofit scenario had lower carbon footprint over the life cycle, 7 buildings where the new construction had the lowest carbon footprint. So this means that the general gentle energy upgrade measures can provide significant both energy and emission savings without compromising the expression and architectural qualities. And this is very significant when we look at these cultural heritage buildings, because it's not really an option to tear them down. So that means that we can implement measures that preserves the expression, but also gives some climate benefits. However, we also saw that the features and complexity of each building must be taken into account when designing these measures. When we looked at the buildings where over the life cycle, the renovation or retrofit scenario was not the lowest in emissions, we also looked at the emissions payback time. That means we, as you see in the graph, the accumulated GHG emissions over the calculation period. You can see the graph for the new construction, the green line, starts higher than the retrofit scenario because obviously it requires more materials to construct a new building than to upgrade one. But the black graph, the retrofit scenario, rises much more quickly than the green one because for each year it has a larger energy demand because the modern building is more energy efficient. And after a while, the graphs cross each other, which means that that's the point in time where the new construction is more climate efficient, so to speak, compared to the retrofit scenario. But that takes, in this case, 44 years. And when we take into account the time that we have left to limit global emissions and reach our goals as a society, we do not have 44 years. And this points to the role that the renovation and retrofit might play as a significant climate mitigation measure, even though over a longer time period, it's not regarded as more beneficial for climate, because we have to take into account that we are running out of time. We also looked at a study that was mapping age, building type, and cost of demolition for buildings in 2 different Norwegian municipalities as sort of an extension of this study, to trying to assess how much emissions might have been avoided if we do not tear buildings down but upgrade them instead. We have to look at the cost of demolition because it's only relevant to calculate this for the cases where the buildings were torn down but replaced by the exact same building function, as opposed to, say, densification, or the buildings burnt down, or they were replaced by roads and such. But when we look at the cases where the buildings were replaced by an exactly same function building, the same, not the same size, but the same function, as opposed to, say, replacing it with replacing one small residential building with a larger one, say, for densification, we saw that even so the buildings were increasing in size. So for new residential buildings and cabins, where it's reasonable to assume that we are fulfilling the same function with the same amount of people, they were almost twice as large as the demolished buildings that they replace. And if we then assume that we renovate buildings, if we also increase the building size, that would erode much of the environmental benefit from renovation. Of course, this is not as easy to assess with non-residential buildings, but it is a very important finding because it points to that consumption cannot increase if we want to reduce emissions. We can't rely on efficiency alone. So when is building preservation a climate mitigation measure? Of course, it depends upon the scope of measures, the efficiency of the energy system, and the specific preconditions of each building. I've included 2 clippings from Norwegian news sites here because they point to that it's easy to assume that retrofit and renovation is always better for the environment, but it's only the case if we significantly lower energy demand. And Norwegians are very happy to refurbish their buildings. We spend an amount, 83 billion Norwegian kroner each year, which is the same amount that the Norwegian state spends on infrastructure. So we need to ensure that we reduce energy demand, and the renovation of the existing building stock can be a relevant measure because we have very limited time to reach our national and international emissions reduction commitments. So retrofit extends the building lifespan and postpones the need for new construction. The materials required for retrofit obviously they cause relatively little emissions compared to a new construction. So targeted energy retrofit can provide emission savings with nearly zero payback. Thank you.
That was a really nice closing, Mie. Yeah, quite interesting. I think we'll take some of those issues up in the discussion. Now we had one researcher and one practitioner, and then I have a researcher who has recently taken a step out into practice with his own tool. And our next speaker is Eirik Resch, and he comes from Reduzer, which he will introduce here, his startup. Please, Eirik. And Eirik has a PhD in industrial ecology in architecture, right? And in math. So quite interesting. His master's degree is in industrial ecology.
Yeah, correct. Thanks, Edgar. So, hi everyone. I'll tell you about the new tool for performing carbon assessments of buildings and infrastructure, which is called Reduzer. It's an online tool that you can find on reduzer.com. My name is Eirik, and as Edgar said, I have a master's degree in industrial ecology. I also have a PhD in architecture and applied math from NTNU and DTU. So I took that work that I did in research, and since we don't have much time to address the climate challenges, and I wanted to move this into practice. So I started a company, Reduzer. And Reduzer is a tool for practitioners, but is also used by a number of researchers. So there are upcoming research papers that have been using this tool as well. It's mainly for spreading it out into practice. So it makes it simple and accurate to do carbon accounting, helps you calculate, work on reducing emissions, and then report it easily according to whatever scheme or environmental ambition that you may have. So this started with my research in that I ended in 2020. I'm still working part-time as a researcher at NTNU, but mainly with developing this software and the company that I founded in 2021. So I've been working on this now for exactly 2 years. It's a 2-year anniversary. This year we have expanded with quite some new people, and we have now 10 pilot customers that are using this tool as their main tool. Next year we will launch widely in Norway, and then we'll spread out to other countries in Europe. So just a few words on this research that is the background for this software. Is my PhD that you can see here on the left side, and one of my main papers. This was also applied into a Norwegian certification scheme, or a voluntary program for environmental buildings, which is called Future Built. So I'll just say very briefly a few words about this. It's a scheme for both calculating emissions with the dynamic LCA, and also sets a number of requirements that you can also call limit values for constructions in Norway. So these limit values, they take into account that we need to rapidly reduce emissions, so they're getting stricter each year that goes until 2050. So they get stricter quite rapidly, and we need to do these changes quite fast. So in this method is a dynamic LCA method that takes into account how things change over time, and that the measures that we do today are more important than what we do 100 years from now. But back to the software, Reduzer. So now I'll just explain a bit more about that. So Future Built is one of the methods that you can calculate in Reduzer, but you can actually calculate with any preferred method, and you can create your own calculation methods here as well. So you can apply it to any certification scheme for any country. There is a big need in the practice for a tool that helps practitioners better apply this on buildings and infrastructure, apply LCA. So the three main challenges that this can be, where this need for a tool can be explained, is that we need to get information about the building into the tools, and we need to connect the right environmental data, and we need to get the goals out, the goal achievement out in reports and in dashboards, so it's easily communicated out to the practitioners and the rest of the industry and to the governmental agencies. So Reduzer solves these and makes it easier to do them, and is also a tool where you can work practically on how to reduce emissions. The first one of these, to get information about the building into the tools. We have different ways of doing that throughout the different planning phases. So in Reduzer, you can follow the project from the earliest concept, early design, and through out all the rest of the planning phases until the final building is there, and you need to document it to, for example, governmental agencies. In the earliest phases, we use a lot of estimated data, generic LCA values, and estimated data for quantities as well. This is gradually replaced, so that at the end, when you have the final building finished, then you'll ideally be left with only project-specific data. In the earliest phases, we can use our early phase estimation tool. So there's very few parameters that you need to enter here to get a complete view of all the emissions in the building. Because in the earliest phases, there's very little information available, but it's also when a lot of the most important decisions are made. So then it's important to get a complete view of the entire system boundary, all the emission sources from the earliest stages. We're also working on BIM integration from the 3D models, since architects and engineers are using BIM models from the earliest phases. They should also be able to rapidly iterate their BIM models and immediately see the results in Reduzer. So when we're working with these LCAs of buildings, carbon assessments, then we need to evaluate different alternatives, and we're making that easy to create different design alternatives and actually compare then what the impacts are of the different ones and which one you should go for to have a better environmental footprint. Second one, we need to connect a lot of different data. So because there's a lot of different data sources, and we organize all of these into our own product library and make them comparable as best as we can. Make it easy to choose and compare the different products. We recently included thousands of products from one Norwegian database, and we are constantly integrating more databases. Third one here is a goal achievement out in dashboard and report. So you can choose any environmental scheme and you get the results for that immediately. So you don't need to actually go through all the details of what should be included and not, and how should it be calculated, because that's done automatically. And you don't need to choose one either, you can choose many. Here are some examples from Norway, but it could be other schemes from any country. And there's no extra work in doing that for different schemes. You just enter the data you want, and you get all of that out in the correct format in reports, PDF reports, or dashboards. We have 10 pilot customers now that we are working closely with to improve the tool. One example here is Norway, where we actually wanted to map the exact product data from EPDs for the exact products, and wanted to do that automatically. So we made a solution for mapping the GTIN number. It's an international product identifier, and the Norwegian version of that, which is number. So the actual EPD numbers can be connected quite easily for the data. If you, for example, have an economic accounting, you will have this product identifier. So there's here's a bunch of reasons why to choose Reduzer, but instead of going through those, you can go to reduzer.com/signup if you want to get in contact. Instead of going through all the rest of the benefits here, I'll just quickly show you the software. Reduzer.com. So I'm just logging in. Here you can see my different projects. You can see the product library, different product categories. You can search for different products. You can compare them by selecting them. There's a component library with different types of building components. So you can easily assemble a building based on, for example, selecting a wall type instead of the exact product. And we also have templates or building archetypes, actually, for some building types. And we're constantly adding more of those, so then you can really easily create a new project. Here is one example project. So when I enter this, here we can see some alternative designs throughout the design phases. Here we can select which environmental scheme that we're using. We can easily switch between them, and the results will be updated. If I open one of these designs, then we can see that here I've added just one component, which contains 4 products. This is 500 square meters of beams. So this is just a random example that I just added right before now. We can here also switch schemes. We can also go into details on the calculation methods. on the system boundary, and on the limit values as well, that we can see the limit value here. So the results are constantly shown live. As you do changes, you will immediately see the results both in the dashboard and inside the workspace where you're working. So here you can also compare, and you can switch out products to see the effect of it, and so on. So that's what I had time for. Thanks.
Thanks a lot, Eirik. Yeah, quite interesting. So the EPDs come back, right? This is data source that we discussed in the first session. I also found it interesting that you had this temporal dimension. If I can also ask the other two speakers, Mie and Sahin, to show themselves, because we're going to have a little bit of a discussion before we invite other people in. I thought it was quite interesting because the dimension, the issue of time came up in all three presentations. For Sahin, it was more backward looking, like what's the building cohorts that we have and the different architectural style. If you do a building cohort modeling, of course, you need to take that into account. The energy standards that existed at different times when the buildings were constructed that are important. Whereas both me and you, Eirik, showed us calculations into the future, because of course these buildings have a long lifetime, and then we make specific assumptions of how the energy mix develops or doesn't change, right? I mean, that's one question, and how to take that into account in the LCA. And there was Tasrin in the Q&A pointed out, well, the EPDs, you know, they don't really look at the demolition phase, and so because it is so far in the future, right, and we don't know, actually we assume a 50-60 year lifetime, but the building probably exists for much longer, and so this just moves out of our consideration horizon. So I wanted you to reflect a little bit about this time dimension. And of course, I agree with Mie that the things that we do now are really important, because the energy is probably going to decarbonize over the next 40 years, right? And at that point, like the higher energy use from the retrofitted buildings maybe isn't so important, at least from a climate perspective. So I'm not sure who would like to take this up.
I can start. So I just want to say one word on EPDs first. So in Reduzer we have EPDs, because EPDs are required by standards, by governmental standards and so on. They want the EPDs. Some of them are very accurate, some of them are less accurate, but that's what they require. You can also use generic values in Reduzer. So you can actually choose, and that brings me to the next point that you asked about, because calculation methods, and it also brings me back to Freja's presentation, that once we set some requirements for the government, then we need to follow those, and it's difficult to change. Well, I think at least it's important to make it easy to use different types of calculation methods and schemes and system boundaries and data, so that we can see the effect on it. And if it's difficult to do that, then people will only follow the requirements. But if it's really easy to switch between them, then we can see the effect in the different schemes, and it's easier to actually evaluate the performance in different schemes and data. Yeah, so I think that's important. But for one of those things that one can investigate is the time impact with dynamic LCA, and as long as it's easy to do it, like we're doing it, then taking the temporal effect into account of how production emissions will reduce going forward into the future. Transportation emissions are really being reduced, and they will reduce more into the future, and so on, and carbon capture and storage. And you can take those different scenarios and see how that will affect it quite easily. So even though those things are very uncertain, like how those will develop, the biggest uncertainty is assuming they will stay constant. That's how I think about it. Like, it's saying that everything will stay the same like it is now for the next 60 or 100 years. That's definitely not the case.
Yeah, right. Good.
Exactly. I agree with Eirik here, and when it comes down to it, we know that there is no one single truth when we estimate emissions into the future. Is one of the reasons why the Norwegian standard for greenhouse gas emissions calculations for buildings requires you to use 2 different scenarios for emissions from electricity, and it comes down to that it is sort of a value choice from the practitioner, which can be said as a case for using weighting factors for weighting emissions that occur in the immediate future heavier than emissions that occur further into the future, because we know more about what is occurring now and what has occurred already than what will occur. So I think that, the method that Eirik has been involved in introducing with Future Built in Norway, where actually time weighting is introduced, I think that is a step forward.
Very good. So with all this focus of the EPDs and the LCAs and the higher level studies that point to the importance of the materials and the construction process and the design, do you, from your experience, feel that has an impact? Do decision makers take this into account? And if yes, how? I mean, this goes mostly to me and Eirik from your experience.
Well, I wish that decision makers, governmental decision makers had taken this into account to the extent that they have done in Denmark. Okay. Unfortunately, we haven't really seen that, although the entire industry has said that the industry is ready to reduce emissions, that we could have emissions requirements for new buildings, and that we have the data. But it is a political barrier, I think.
Mm-hmm.
It is being required in more and more countries, and also on the European level. So it's going to come, but the question is just like which exact year it's going to be put into force. But it's definitely coming, and the entire industry, especially in Norway and some other countries as well, are very eager to get started before the requirements get into effect. So it's definitely coming. Yeah.
So, but you think that a legal requirement is required and like a target value or something like that?
Probably that's. I think that's a good way to go about it. But then we need to assess the uncertainties. Of course, that's the question. So. We need to have a good methodology for calculating it. That's a very standardized method, so it doesn't leave much choice to make scenarios, and it also needs to be the same for the data. So we need to have good data at the bottom, EPD data or generic data. It needs to be sufficiently accurate, and I think it is today. I think it is sufficiently accurate so that we can set requirements. There is of course uncertainties, but I think we can start setting the requirements already.
Right. I wonder whether any of the earlier speakers would like to come in here if you are interested. So with that we actually see that the EPDs, it seems like here the EPDs have sort of become a very important thing as a data collection, as something where companies can provide information to users. But there's like the environmental footprint methodology from the EU. That tries to be a little bit more open and more standardized than maybe EPDs are. And there's normal LCAs. I wonder whether you have any reflection about these different approaches that are being taken in the building industry.
I could say that one thing about the European system is that it's not established for the construction products in the way that EPDs are. And I think although we recognize that the weaknesses of EPDs, they might be inaccurate, they might be outdated, but broadly speaking, it gives a good picture, and that we should work to try and increase the quality of the EPDs rather than changing to a different system, because we really, really overdue with introducing requirements in the first place. So if we work to make EPDs as best as possible, then I think that's a good way forward.
Yeah. You try to improve the system while you go along and use it. I think you're saying, and that sounds like a smart strategy. Freja, you were next.
Yes, I agree.
We can hardly hear you.
Yes. Okay. I agree. We need to run on parallel tracks here, like following the rules. And as Eirik pointed out, we should still be able to see what if the method was slightly different and if we viewed it in another way. But the rules are now set, and we know from several EU legislative preparation and legislation in preparation, we know which direction it's going in terms of methodology and in terms of scope. So these are the rules set out, and these are the rules that the building regulations will have to adopt and adapt to when they integrate it. But then, as researchers, of course, also be critical.
Niko?
Yeah, just again, I talk from a very convenient position because in Switzerland we have calculation rules for environmental embodied emissions in buildings for quite a while, and actually I was recently interviewed by the EPBD, like the Energy Performance of Buildings Directive from the European Union, because they want to establish something for the EU as well. And I think it's very important to think also about how we get these things implemented. I think Eirik gave a bunch of examples, but I think having a standardized way to calculate and to have like the rules set is very, very important. And for us, it's a huge advantage in the city, within the city administration for the buildings. We have a huge advantage because we have clear rules where we can do the calculations and like clearly say these 12 kilogram per square meter. That is it's a very tangible number for us. When I look at civil engineers or other tunnel builders and so on, they are completely overwhelmed right now. So I think it's very important to push forward these standards.
Very good. No, Carine has raised her hands. I actually want to bring up a different issue, and it seems like you all have become experts and you're involved in something that's very exciting and happening now. And so I wonder whether you have any advice to somebody who would like to get into this field. Is this a smart thing to do? And what are the pathways? And what would you look for if you were going to start out today? And so I'm giving it to Carine, whether she wants to take this up or the previous question. That's up to her. And then for the others to think about that. Please, Carine.
Yeah, no, my comment is a bit of a mix, actually, but it goes first on the EPD side. So now maybe it's seen a bit as a black box from the research community, but in fact, if we have the opportunity to crack them in a way, talking about open access of the data, as we do in the research community, then, I mean, the data are back to EPD. So, in fact, if we have access to them, then it's a huge potential, actually. And for advice to engage in this debate, and I think it's we should really see, like it's the case today, as an ecosystem of different competencies. It's not one or the other. We really have to do it together and just start somewhere, and then let's see what the future brings. I would say.
Okay. Anybody else? Yeah, Eirik.
I think this is a very exciting field to go into now because it's a cross between active research. There's a lot going on in the research development, and it's also a very real issue that we need to solve really fast. So in this cross between developing research continuously and actually getting it quickly into practice, this is a very, very exciting field with a lot of opportunities during the next couple of years.
Good. Niko, final word. I think we're...
Oh, sorry.
No, we have another 2 minutes, but...
Again, maybe more the applied viewpoint. I think something I'm realizing more and more is that the architect is really like a little bit like the central point in the whole thing. I think if you want to specialize in the field, learn their language or become an architect who is also capable of doing environmental calculations, whatever. But I think it's very important because they always become like the central node in all these issues. Yeah, that's my take on this.
Yes, I see that Sahin is listening attentively here. Anybody else? Well, Sahin.
Yeah. As a person who comes from the architectural background, I mean, I think the inclusion of those environmental issues in the curriculums is quite important because we are in the position of sometimes in the main decision maker in the projects, and our collaborations with the different professions starts with the education of the architects themselves. I think I would have a different kind of mindset if I have introduced those kind of topics earlier in the bachelor years. But right now also in the architecture field, a lot of master programs and the PhD programs which are focusing on sustainable architecture, use of computational tools, environmental performance of buildings are included. So I think it will create a great opportunity in the future.
Right. Well, it was my intention to finish now at 11:50 my time. We have another 10 minutes before the next session starts in the International Industrial Ecology Day. So I would like to thank all the participants and the speakers for what I thought was a really interesting discussion here and nice presentations with